Hello, IoT Builders. Welcome to a new episode of our live stream where we discuss a range of topics on the Internet of Things, from embedded devices to cloud services, all from an IoT Builder perspective. It is July 19th, and this is episode 37 of our weekly live stream. My name is Alina, and I'm a senior developer advocate for IoT at AWS. And today we are going to cover some really interesting topics around microvisor and next generation IoT architectures. And joining us to discuss these topics are Jonathan, Principal Product Manager at Core, and Randy, Principal Software Engineer at Core. Hi, both.
Hello.
Hi, Alina. Good to see you.
Hi. Good to see you too. How are you doing?
Yes, very good. Thank you. Very good.
That's nice. So could you both introduce yourselves briefly, please?
Of course, yeah, I'll go first. My name's Jonathan Williams. I'm in product management at Core, where I look after what we call device builder platforms, which includes a number of products, but obviously the microvisor architecture that we're going to talk to you about today. Prior to kind of joining Core, and I guess several years ago, I was an embedded software engineer. Primarily working in the Bluetooth and audio space, so sort of low-level software for Bluetooth, application-level software for Bluetooth, and I kind of bring that embedded software engineer background into everything I kind of do, and we do for the IoT builders of the world here at Core.
Yep, and I'm Randy Biter. I'm a principal software engineer on the device builder team at Core. I joined Twilio about 8 years ago, and for the past 5 years, I've been working on the device builder team, helping on both the connectivity side and the device side to bring IoT applications to the world.
Very nice. Thank you very much. Yeah, so I'm actually really excited about this topic. And the first thing that I want to ask you is around the problem space, right, and the challenges. So what are the general challenges in embedded development? And what is microvisor, and then how does microvisor try to solve these challenges?
No, exactly that, and a little bit more background. So, at Twilio, the Twilio IoT and Wireless group that's just been acquired by Core. Prior to that, we acquired a company called Electric Imp, and the Electric Imp product was again an IoT builder. Platform style product that's been in the market and around for a number of years, so pretty much 10 years now. So the team that we have building out these products in the IoT space have been working in the field of IoT and IoT devices, connected devices, and secure connected devices for a number of years now. So I think it's kind of fair to say that we've seen many problems and challenges when it comes to building IoT devices. I could probably spend hours going into them, but I think some of the main ones that kind of we really see very regularly, I think is that it's kind of quite easy in today's world to build one device that connects to your application, be it your something you've got at home, be it a server, be it even something like AWS IoT. It's quite easy to get one device, get some example code, get up and running, and away you go. And you might feel as though you kind of have an IoT product that's not far off being ready to go. But I think what we've really learnt over those years, with the Electric Imp product and now microvisor, is that it's very different. The expectation in terms of uptime and connectivity and robustness and reliability and security, all of those things that people always talk about is very, very different when you're deploying, one device on your developer's desk to deploying, thousands, tens of thousands, hundreds of thousands, even millions of devices out there in the field. So actually making products that are, robust and reliable and maintain connectivity for, many, many years is kind of the real challenge. And when you look at the kind of the scale of that challenge, what do companies typically do? And typically, you might build your application, you might build an embedded device, you write your device side code, you maybe have some cloud code, you connect the two together, and away you go. And then what happens is you kind of spend the next, 5 years, 10 years, frantically trying to support and maintain and fix all of the issues that are in those products. and that itself is kind of really expensive. It's really expensive to support and maintain a fleet of products that are out there in the field today. And with that, you end up with, a large team, perhaps a lot of technical debt, a lot of challenges about the design decisions that you made on day one that you now have to live with for the lifetime of your product. And those, I think we probably all know companies, or maybe even there are people here, who have built products that they end up having to support for years into the future. And that itself is kind of a big challenge. So, we've taken everything that we've done with the kind of electric imp platform and the many millions of devices that have been built for that platform over the last 10 years or so. All of the knowledge and experience that we've had around what our customers were trying to do and the kind of problems that they've had. That's really, sort of driven our approach, and specifically the architecture that a microvisor approach really brings to this space. And as we go through, some of the things that a microvisor approach enables you to do, then you'll see how it kind of really addresses some of those problems around, maintaining fleets of devices and that kind of longevity of support, making sure they're connected reliably and they're secure for the lifetime of the device. All those things that everybody says they want, a microvisor approach, I believe, is kind of a brand new way of solving that problem that will become the kind of de facto approach for architecting IoT devices in the future.
Yeah, that's interesting. I mean, what do you think that makes microvisor so different than to the other things that came before it?
It definitely, and I think probably, I'll be completely honest. People in the IoT space use the word platform. I use the word platform, and the word platform, it has lots of different meanings. Most of them pretty rubbish. But essentially, lots of IoT platforms have existed in the past, right, up till today. And including in that is our own electric imp platform, right? We had a platform approach to IoT. There are others, from many other companies that have kind of tried to build out device-side IoT platforms. I think it's fair to say that all of those platforms, if you look at them from a high level, are all kind of the same, right? They basically all force you as the embedded developer to adopt the ways of working of the platform. You kind of have to bend your approach to what the platform mandates or defines. So if we look at the electric imp platform, then you have to write your code a certain way. You have to use a certain language. You have to use certain APIs. Now, if that language and that environment and those tools and those APIs all, you're happy with all of those design choices, then great. This platform solves all of the IoT problems that you want it to solve. But so often, a device development team, the embedded software engineers, hardware engineers within companies that we speak to, they actually already have their ways of working. Sometimes it's because they've been in the industry 25 plus years and, they started off using tools 20 years ago and they don't really want to change. What's wrong with that? Sometimes it's because a company has some code that they brought in from somewhere else that they need to reuse. Nothing wrong with that. There's a whole load of requirements that come into a project or product that are kind of hard to move away from. So IoT platforms kind of force you to choose between, the reuse and reuse of experience and reuse of code that you've got versus going all in on the ways of the platform. And then on top of that, if you go all in on the ways of the platform, you're kind of beholden to the where does the platform go? What if the direction of the company that sold you the components that you use in your platform piece, they change plan, or what if you want a feature that the platform can't provide? All of those things kind of force you as a development team to take risks in building your product. And when we consider that you want your product to last for 5-10 years, as some of our customers do, then that's a big risk to ask any team to take. You know, and every IoT platform has really said, you know, if you do everything our way, don't worry, it'll all be fine. And I personally, I look at that and go, you know, as my past as an embedded software engineer, and I imagine Randy would say the same, you know, that's not a risk that I'm that comfortable in taking, right? It's a, you know, it's lovely if it works, but what if it doesn't? So the real difference in a microvisor approach is that the microvisor approach itself separates the connectivity stack, and we'll talk a little bit about how we do that in a while, but it separates out the connectivity stack and the maintainability of the device and the security, you know, all of those kind of boring but necessary system components that every IoT device kind of has. It takes all of that and runs it separately from your firmware, your application. So your firmware and your application essentially is kind of the, you know, the cool bit, the business logic of your IoT device. You know, that can now be anything you want it to be. So it can be any operating system, it can be any programming language. You get direct hardware control access to the hardware that's on the device itself. So essentially, you know, all of those design decisions that you want to make about your application, your architecture, your on-chip code, you can make all of those choices exactly as you would without using microvisor. So as a platform, again, to go to that word that I said, like, you know, as a platform, it really is kind of decoupling the kind of platform, you know, expectations and requirements from the application and the firmware side of things. And so what we find is that, you know, customers or prospects really value the fact that they own all of their code and can control all of the design decisions, tool chain decisions, you know, operating system decisions, you know, all of that they continue to own. And there's almost no requirements from you know, from a microvisor point of view as to how you write your code. And that, I think, is, you know, is one of the ways that a microvisor architecture or approach is kind of completely different to almost every other IoT platform that's gone before, really.
So this basically means that the developer experience while working with microvisor is not really so much different than it normally would be when writing an application.
Exactly that. So if you have, you know, toolchain development environment or you know, existing libraries or code, you know, maybe you live in an ST world and you want to use that toolchain. You know, maybe you live in a world where you want to build on top of FreeRTOS and use all of the libraries and components and everything that you get from the internet. Or maybe you've got some homegrown scheduler that you've been tinkering with for the last 15 years, and it's now so tightly integrated into your application and the way your product works, you want to carry on using that. You can do all of that, you know, any one of those approaches. And, you know, if I look at what customers are doing today, I would say, you know, the majority are probably using or looking to use, you know, an off-the-shelf operating system, mostly FreeRTOS. You know, so you'll see that, you know, most of our example applications and demonstration applications are kind of built on that. But we also see people using Zephyr. We see, people using all sorts. So, you know, I've even got somebody who's looking to use a .NET port to the ST chip, which kind of sounds crazy, but that's what they want to do. And, you know, as long as you can run it on an M series core, then you can run it alongside microvisor. And now microvisor takes care of all of the connectivity pieces, and you just write your application. And that is pretty cool, I think.
Yeah, that makes sense. I mean, I'm actually curious about the architecture of microvisor. So, you know, it would be good if we could talk about that. And then the next question as a follow-up would be, how does an application actually interact with microvisor?
Sounds good. Yeah. So, and if you want to put a couple of slides together. So essentially, you know, a microvisor, you know, I think what I believe is, you know, whether it's our microvisor or whether it's somebody else's microvisor architecture that ends up being the approach that the world uses. You know, I think that this approach to building and securing IoT devices is kind of the right way to go. And the way that this works really, and what we kind of see this is it's kind of a hardware enabled hypervisor for microcontrollers. So it's, we've kind of crashed hypervisor and microcontroller together to come up with what I'd like to think could be an industry standard term called microvisor. So that approach itself kind of is built on in this case an M series or M33 based core in the STM32U5 family of ICs, and we actually use the ARM Trust Zone component or the ARM Trust Zone hardware, which typically people use for separating out little bits of security acceleration code. But rather than just separating out that sort of security acceleration code piece, which you might normally do, what we're actually doing is we're using that hardware to completely separate the MCU core into two zones. So the application zone, which, as I said, can be anything you want it to be. Let's say a FreeRTOS based application, running all of your code, your libraries, whatever it is you want to do. And then separately, separated by this trust zone hardware, there's the microvisor zone. And rather than kind of just run, security accelerator type code, what we actually do is we run the kind of full microvisor stack, which includes everything that you want security wise. It includes the device drivers for your connectivity components, so be that Wi-Fi or Ethernet or cellular modem connectivity, and it includes the IP stack that's running on that device. So essentially, everything that your device needs to get online and stay online is now logically in those red boxes in the microvisor zone. And what that really means is that whatever your application is doing. So if we imagine the worst case scenario, that your application, you've deployed a fix to your application, you've tested it on your desk, it seems to work. You push it to 10,000 devices, and now 10,000 devices, the application crashes on boot, right? Because there's some nasty bug in there that you didn't notice. That would be a disaster, right? If you have a fleet of devices. But with a microvisor-based architecture, that's actually not a problem. If we imagine a scenario where the application code has got stuck in some loop on startup, or FreeRTOS is failing to start properly or something, then in a microvisor architected world, because the microvisor piece is online and connected and has everything that the device needs to stay online, then it doesn't matter that your application is not working. Everything your device needs to stay online is managed by microvisor. So now, rather than have a product recall and have to send engineers out to change hardware because you messed up, now you can use the microvisor path to flash an entirely new application or a fixed application or maybe the old application onto your devices, and you're back up and running in no time. And that sort of the logical split between connectivity and your application, I think is increasingly going to be a must-have requirement in IoT devices. I think we've all seen examples of, the kind of monolithic application with operating system, connectivity, everything application all built in together. And if that goes wrong, your device is unreachable. Whereas separating connectivity to the application, I think is a really great way of kind of building robust IoT devices. And that's what a microvisor approach really, really brings. And as I've said, you can build on any application code you want, because now the application is separate from the connectivity. You can use any tool chain that you want, and you can because your code is essentially running natively on the ST chip or on the core itself, then any access to hardware, you get direct access there as well. So it runs, essentially near real time. Obviously, connectivity events can still come along and interrupt the flow of your code running on the application side. But that would happen anyway, even in a monolithic app. But essentially, your code sits on top of the hardware, as if the microvisor wasn't there. And we do have some use cases now where people are using the microvisor to push code to their devices, where their devices have no knowledge of there even being a microvisor on the device, which is pretty cool. and they're just using it for kind of over-the-air firmware deployment reasons, really.
Yeah, so that's really interesting. Would we be able to walk through a really easy scenario? For example, let's say we have a small application that tries to send an MQTT message, for example. And what would the application be responsible for, and what would be the microvisor responsible for, and how would the application communicate with microvisor in that scenario?
Yeah, sounds good. Randy, do you want to go, or do you want me to?
Happy to.
Go through it, Randy. Cool.
Yep. So we have a couple of communication paths for microvisor today. They're both managed and passed through our cloud infrastructure. One of those is a managed HTTP route, and one is a managed MQTT route. So for the use case that you've described, we would set up the configuration. So we support either username and password configuration or certificate-based configuration. We've tested that out against AWS IoT and a number of other brokers or self-hosted brokers. But you would be able to configure those credentials on a device-by-device basis. And we have a configuration and a secret store managed in the cloud where you can push those per device credentials or just per account credentials as well. So say you could configure the MQTT broker at an account-wide level and then have each device have its own credentials. So in your code, you would spin up the managed MQTT client. You'd pass in that configuration as to where your broker lived, what port, any certificate bundles if you're doing custom certificate authority on the back end, as well as the credential information. And then you're able to subscribe and publish to any topics that you want. We support both MQTT 3.1.1 and 5 versions, so you can connect to a broker on either of those versioning schemes. And you can just publish that information up. You can also subscribe to topics if you want your devices to receive messages and then go offline for a while for power saving reasons, come back on. You can receive those at a later time using using MQTT standard quality of service levels.
Mm-hmm. Okay, that sounds good. And who is actually managing the connection? So the connection to IoT Core, is that happening directly from the application to the cloud, or is it happening from microvisor zone to the cloud?
Yep. So it's in the microvisor cloud. So the way that the communications work for user applications is it's all proxied through the microvisor kernel, and then that kernel maintains a single connection with multiple streams within it to our cloud. So the broker actually connecting is going to live on the cloud. That allows for that connectivity, the connection with the broker, to be a little bit more stable than cellular in some cases can offer. And it will stay connected while your application has told it to stay connected for those subscriptions and proxy those back down to the device.
Okay, so you can't have situations where the device is unreachable and you're still trying to do something. This prevents devices following firmware upgrades, devices reaching an unusable state while they're somewhere remote. Yeah, this is really cool. Very interesting. So before the live demo, because I know that, Randy, you have prepared a really interesting live demo for us. So I'm wondering, Jonathan, is there anything else that we should cover before the demo? What do you think?
Well, I think probably as, I guess, a bit of an introduction in terms of the demo itself. So yeah, so one thing that this architecture really enables, which I think is super exciting, and the reason I think it's super exciting is that I don't think there's any other anything else out there that kind of achieve the same same capability. If I've described how the connectivity and the application are separated by the trust zone hardware, and I've kind of described how even in the worst case where your application is not running or it's crashed or something's gone wrong, the microvisor zone is still running online and connected. And one thing that we've kind of used that for or enabled is that we can actually tunnel the GDB debug protocol across the cloud connection. So whether that's via Wi-Fi or Ethernet or cellular connectivity, we can tunnel that from your developer's desk or your desk all the way to one of your devices, to the microvisor zone, and then we connect that up internally in the IC to the on-chip debug hardware. So what we've really now got is the ability for you as a developer to completely debug a device anywhere in the world. And that feature itself, I think is pretty exciting. It enables a whole bunch of use cases which we can go into a little bit later. But really just being able to kind of single step your code, your application, your firmware on a device that's in the field, halfway up a lamppost in a different country. How would you do that? And the answer is that with a microvisor architecture running on your device, then you can now securely, remotely debug an application that's gone wrong, in the field. And Randy's going to kind of walk us through an example of how that works, which I think is a really cool thing. If you think of it from your experience as a developer, how many times have you had a customer issue that happens on the customer site but doesn't happen when you test it on your desk? And all of those kind of problems are kind of really now solved with a microvisor approach.
Yeah, so I'm looking forward to seeing the demo that Randy prepared for us.
Right, so we'll jump right in. So what we have on the video camera screen right here is an asset tracker. So this is version 2 of our programmable asset tracker. Version 1 has open source hardware and code available on GitHub. This is version 2. The version 1 was built on the Electric Imp platform that Jonathan mentioned a few moments ago, and version 2 is on our microvisor platform. So I'm not going to be showing any asset tracking examples today. I'm just going to be blinking an LED, the embedded equivalent of Hello World. So you can see that we have 3 LEDs blinking away here. The green LED here is the microvisor system status LED that shows that the kernel is up, happy, connected to the microvisor cloud and is functioning. The blue LED here indicates network connectivity. We're going over cellular right now. And then the yellow LED blinking here is a user LED that's being controlled by the non-secure side of Trust Zone in the user application space. And these wires aren't debugged, they're just power, so I don't burn through AA batteries with the device sitting on my desk. So what we're going to do is we're going to push an update that's going to intentionally crash the application very early on in its life cycle. I'm just going to go ahead and do that now. So I'm on a Mac. Our primary build environment today is under Ubuntu. Pretty much anything that can run the ARM cross-compiler toolchain for this device is suitable. But all of our testing and documentation is around the Ubuntu route. So I'm going to run that within Docker. I'm going to go ahead and do a build. And so this is going to compile the sample application locally. It's basically just a lightly modified version of our FreeRTOS demo. It's going to package that up into what we call a bundle, and it's going to push it up to the microvisor cloud. After that, we're going to send the microvisor kernel a message saying that a new application bundle is available. Microvisor kernel is going to download that and write it to the user application memory and then kick that off. And so we're streaming the logs for that device right now, and we can see already that we have a crash. So we have a crash report, CPU fault. So a couple of other things to mention with that bundle that we sent up to the cloud. So you'll notice up here that it says it's writing a public key and a private key. There's a key pair that we're associating. You can do this once or you can do this with every build. We've chosen to do it with every build for our demo, just to make sure that each build is linked to a particular ELF file to make debugging a lot more obvious, and you don't end up trying to connect to a device with the wrong ELF build locally and have GDB get confused. So the public key is being sent to the cloud and is also sent to the device, and then the private key is kept locally. This ensures that only connections, regardless of having the credentials to connect to your microvisor cloud account, only those in possession of the private key can actually get in and debug the device. So we have a very nice crash dump here, which gives us a lot of the information I'm going to show you in GDB. I'll skip over this because I'd like to show it to you in GDB live and then also show another example of that remote debugging. So we'll go ahead over here. So the first part of our GDB setup for remote debugging for a microvisor is to set up a proxy between your local machine and the microvisor cloud that GDB's remote targeting can connect to. So again, we're going to run that under Docker as well. I'm going to set up a local network for Docker so we can share this instance of this proxy with another run of this container that's just going to run the GDB command for us. And we're going to pass in the device SID. I've got that set in the environment. And we're going to specify the that private key that I mentioned. And we'll make sure we see it listening. Okay, so the GDB server is now listening on port 8001 on GDB-server within that network in Docker. We're going to go ahead and also run within that same Docker instance and connected to that same network, a just standard GDB pointing to that ELF file to load the symbols from. So the first thing we're going to do is set up remote timeout. The cellular connection here is pretty good, but if the cellular connection was a little bit laggy, the GDB remote server connection can time out. So I'll go ahead and set a timeout just to make sure that doesn't happen for us. So I'm going to set a target of a remote GDB server. That GDB server is just named the container name that we gave it for Docker and port 8001. We're going to see that we're presently crashed. I'm going to go ahead and continue this and restart the application via a REST API call. So we'll continue running. I'm going to hop over here and issue that, that post against our microvisor API. You see the error code was 0, meaning no error. And we can see we have the location of a segmentation fault. So if we try to do a backtrace, we're not seeing anything, which gives us a hint as to what's happening, but we'll go ahead and drill into the registers just to verify what we think is happening. So we can see it's in the vfprintf file in the libraries, and we can see that we were trying to print out our debug ping message. Let's take a look at those registers and see if we can glean anything from those. Up here, we can see a combination of both user application space and kernel space, a microvisor kernel code running here. But let's take a look at what the actual faults are that we're seeing. We can see we have the hard fault status register has a value in there. I'm not going to run you through the entire 2,000-page data sheet, but I will drill into a couple of bookmarks that I've set, which have the registers that are useful to us for today. And I wasn't kidding about the 2,000 pages part. So the hard fault status register, right over here, is going to show us, we're going to see what the root cause was, or at least the best indication of what the root cause was. So it's a 32-bit bit mask field. And if we count through, we'll go 8, 16, 24, 28. And then the third bit within that last nibble is set. So we've got 31 by my counting. So 31 zero-based is going to be this forced flag. So we can drill down and check that out. Indicates that a fault with a configurable priority has been escalated to a hard fault exception. So that probably means that our configurable fault register is populated, and indeed it is. So if we check the documentation for the CFSR and try to decipher what that one is, we have CFSR right there. So we can see that CFSR is made up of 3 individual registers. The memmanage fault status register, that looks like it's 0, so we can bypass that one. The bus fault status register is the next byte, and that also is 0. Then we get to the usage fault status register, which is 2 bytes, and that actually does have some value in there. So we lost the 0 padding for that, but it looks like the 5th bit is set for that status register. So let's look at the documentation for the usage fault status register to see what's going on there. So we can see the fifth bit, again, 0 indexed, is STKOF, which sounds a lot like Stack Overflow. So we also saw this mentioned when we tried to get a backtrace of where our crash was to see who the callers were. And I'll go ahead and run that again. So we can see that it's also calling out that we might have a corrupted stack. So let's take a look at the code, specifically where we're trying to emit that ping debug message and see if we can figure out why that's happening. So search for that ping. We can see that we're calling a method that we've defined called server log. Check out that function, and we can see server log and server error are kind of doing the same thing, just posting a Boolean of whether this is just a log message or whether it's an error message. But the real work is being done in post logs. Let's take a look there. And we can see in here there is a VSN printf where we're taking those variable arguments and kind of compositing those to a string and then sending it off to a microvisor syscall. And I'll get into syscalls in a little bit if we have time. So we can see we're creating a buffer here to composite that message together. And that buffer size is defined by log message max length. So let's take a look at the header file and see what we've got that defined as. That's being defined as 1024 bytes, pretty sizable, and that's probably going to be pushing against the default stack size that we've configured for our free RTOS tasks. So if we take a look back at our main file and head up to see how we're defining our two tasks, we have one task that's blinking the LED as a GPIO task, and then we have this thing we call work task. We can see we're using the config minimal stack size, which I've got set up as 1024 words. So I'm just going to give it a little bit of headroom here just to see if we can get that to work and not crash on us anymore. So let's go ahead and push some new code and see if this actually fixes things for us. So I'm going to terminate our GDB session here. As I mentioned before, by default, the demo applications regenerate that key pair every time. So our proxy is no longer going to be valid after we've done this. This particular GDB instance wouldn't be valid because we targeted that ELF file, but then the proxy is also going to become invalid as a result of changing that key out from under it. So I'm just going to exit GDB here. We'll see the proxy goes away on its own when that session is ended. We're going to go ahead and break out of our tailing of the logs, and we're just going to build that application once more and push it up to Microvisor Cloud. So I'm going to show you the camera again. So it's worth noting here that while this has been hard faulted, the user LED froze because it only was able to tick off once, change that status once before we actually had that crash in the logging method. We can see, however, that the microvisor status LED and the networking LED are still happy. And you'll see that the LED is blinking fast there. That's the new code being downloaded over the network. And we can see that, once again, we have a user LED blinking. And we actually are seeing those messages emitted now. So we took care of that crash. So moving beyond that kind of like a fatal crash that, I mean, if the only code running on your device, on your asset tracker here was your code and there was some fatal issue with it, you'd have to hook up an SWD debugger or do something to try to rescue that, switch to a different, to an alternate OTA, whatnot. But this actually allows you to take care of that. Now, we could have rolled back to a prior version, as Jonathan mentioned, or we can, to get a customer device going, or you can do a little bit more debugging into that, like we showed here. I'm going to start up another GDB proxy session. So we've got that listening once again. And this time around, I'm going to set a breakpoint. So let's go ahead and once again set that remote timeout. And then set our target to remote GDB server port 8001. So you can see, instead of a crashed application now, we're actually in one in the middle of FreeRTOS's processing tasks. That's also giving that error, probably because it was called through an interrupt. But let's go ahead and set a breakpoint for ourselves. And we're going to set that on start work task. And let's go ahead and continue execution. So start work task is called when we first fire up the FreeRTOS run loop. And right now we're within a while loop within that task. So we're not going to hit that right now. I'm going to go ahead and restart that application once more, and we'll see that we'll be able to break it right as this task starts here. At the moment, it's inside of this infinite loop. So let's go ahead and send that restart message to the device once more. All right, so we can see that we're actually in there now. And we are at line 6. Nope. Let's go ahead and restart. Yes, we are in the start work task. So I'm going to go ahead and turn on the text UI just so we can see the code a little bit better as we step through it. So right now we're initiating that work buffer that we'd use maybe for some sensor data, you can imagine. The next bit of code that's going to run is going to be to initiate or initialize the count variable. We're going to start that off as 0, but we're going to override that in just a moment. And then we're going to go into that loop where we emit those pings. And you can see up here, it starts with 0 and works its way up 1, 2, 3, 4. So we can go ahead and print out that variable. You can see it's currently set to 0. We can modify that variable actually and set it to a number that a number of folks will probably recognize. Go ahead and continue execution here. And what that's going to do is that's going to let our user application continue. So you can see that Microvisor is still doing its thing, but our user application is frozen. The other FreeRTOS task that we have to toggle the GPIO for the LED is also frozen still because we have the debugger enabled. So we'll continue execution, and we'll see that start to blink. And we'll also notice that we've started our count instead of at 0 at 42 here. And if I'm done with that debug session, I can exit out of that. And the application will continue running as it was. So I will we'll turn it back over to Jonathan at this point.
Yeah. I know, and that demo, I think what I always find interesting with that demo, Randy, it's so cool. But you kind of need to think about what it's actually doing, what you've actually just done there, right? Which is you've done what all of us embedded developers do when you encounter an issue, but you've now done it on a device that's connected completely remotely, in this case over a cellular network, that could be in almost any country, it could be anywhere. And the kind of performance you get there obviously is impacted slightly because you're bouncing those commands via a cellular network. But from a user perspective, you've managed to debug what would otherwise be a totally fatal issue on a device in the field. And as I said earlier, how many times have we had those issues where the customer or the end user reports an issue, but for the life of you can't reproduce it on your desk. And when we look at connected devices, one stat that we had from a survey that we ran was that over 80% of issues that exist with devices are down to that connectivity piece. You work on devices in one country, you deploy them in another, and devices behave differently, right? That is kind of the business we're in. So being able to kind of guarantee that those devices connect, and then if and when they do go wrong, you can get in there and kind of debug what's going on in real time, fix an issue before it becomes a major issue across your fleet. It's kind of priceless, I think. And that kind of ability to do that, I believe that really almost changes, the entire mindset of us as embedded developers. The old way of working was very much you would build your application, you would test the hell out of it, you'd put it on your test racks, you'd run it for weeks, maybe months, you'd have a long, complicated release process. You have to go through all of those steps before you could even risk deploying it to your fleet of devices. Now, I'm not saying you should throw out that entire process, but you could now imagine a world where, the way that we develop cloud-based applications, sort of a more agile approach, pushing firmware fixes to devices very quickly and being able to kind of move fast. We can now do that in an embedded device. a microvisor architecture enables you to push firmware to devices that, even in the worst case, if you've broken it, you can now fix it. And better than that, you can work out why it was broken because you can debug it. Then you can fix it. Then you can push the new code to it. And code-wise, you can do that with, as we talked at the top, code of any shape that you want, be it built on FreeRTOS, as kind of Randy showed in our demo application, or be it any existing code that you've already got. And those, I think, those kind of cool features that really mean that you as an embedded development team or developer can now run your code your way, and Microvisor takes care of connectivity, security, and those aspects. But it means that you can now move faster. You can, you could consider deploying devices with, which aren't feature complete, and then working on the features, over the next year or so, and pushing firmware builds to your devices in the field and upgrading them. All those kind of things that really bring the sort of cloud-based agility that we kind of know in cloud development. You now bring that down to the edge, and I think that's never really been possible before. And a microvisor architecture really kind of enables that agility in kind of a new way.
Yeah, that makes sense. And even things like, A/B testing, for example, that you might want to do. So you might want to test on just a percentage of your fleet, a very small one, to test a different version of an application. I think this makes it super easy to do so.
Yeah, no, exactly. And kind of, almost an extension of that. We've got one customer that's actually decided that they can deploy a device in the field with Microvisor, and they can use that device to then collect data, which they then need to use to inform how they're going to write their application. So, the kind of old-fashioned way of doing it would be you'd have to create a simulation of the environment that your device is going to go into, and you spend the first 6 months building a test harness that simulates the environment that your device is going into. But with a microvisor enabled device, you can deploy that into the field, and you can now develop in the real environment, right, with real data happening in real time. That's never been possible before. So there are whole sort of savings around. Do you need to now simulate or emulate your entire environment in order to write your embedded code, which is how you used to do things? Or can you just deploy devices in the field with the sensors attached, start collecting the data, and then write your application that actually becomes your product? And that approach, I think, is again quite exciting, really.
And what about limitations? So are there any potential limitations as to what you can do inside your application?
Yeah, that's a great question. It wouldn't be fair to me to say no, everything's perfect, because nothing in the world is. So there are some kind of limitations. Obviously, from a hardware perspective today, in our implementation of a microvisor, then we are targeting a specific ST chipset today. So the STM32U585 family of chips today is kind of where we're targeting, and that's a core with an M33 based core, which includes this trust zone component that we use for enabling the microvisor. Obviously, if devices, other devices do exist that support that M33 core and the trust zone hardware, we could support those devices in the future. But today, you're kind of restricted to only using that U5 chip. And then similarly on connectivity, today we support cellular connectivity. We've got a choice of modems that you can use on that. And we support Wi-Fi and Ethernet connectivity via a coprocessor today. But some of those hardware choices are kind of, restricted today or limited today in terms of the choices that you can make. Obviously, there's nothing in the architecture that means that we can't support different bits of hardware in the future. But today, we kind of only support that kind of one real configuration. From a software perspective, that's a really interesting question. So kind of your code, your application runs, as I said, essentially natively on the device. It talks directly to the MCU. There's no shim layer between your code and the hardware, which so many IoT platforms of old would kind of do. But the microvisor code can interrupt, the main application code. It kind of has to, right? It has to service the interrupts for the connectivity pieces, which are kind of higher priority than other things. So, you will find that obviously, your code gets interrupted by microvisor code when microvisor receives a message on the Wi-Fi interface, for example. But equally, you could argue that would have happened anyway, right? Even in a monolithic application, you would have had to have done that. Randy talked a little bit about the microvisor system calls. If you want to start sending data through the microvisor piece to microvisor cloud and onwards to your cloud, then we support a number of ways of doing that. And you now have to kind of start talking to those system calls or function calls on the device to get data, off the device. You don't have to use those if you've got an application that doesn't send any data to the cloud. And, I talked about, a couple of customers that are using this purely for kind of pushing firmware to their devices, and then everything runs locally. But the truth is that I'm going to say most IoT devices do want to send some data off the cloud. Yeah. So at that point, you kind of have to start using some of those microvisor system calls. You can call those from C. You can call those from other languages as well. So there's kind of no restrictions in what you can do, but obviously there is a little bit of a shape to those calls that you need to then integrate into your code. But that sort of level of integration is pretty basic and pretty straightforward. We very much try not to kind of tell you how to architect your application or tell you how to write your code. What we really try and do is kind of enable functions that you need for your device to kind of get online and stay online, but all of the application level decisions are kind of up to you, really.
Okay, so there is an SDK then that is available that developers can integrate in their application.
Yeah. So we provide a slightly modified version of the ST HAL for the U5, and then we provide example apps mostly built on FreeRTOS today that demonstrate the secure remote debugging and a few other things. But yeah, it's essentially you integrate that into your toolchain, your application, and away you go.
Okay. Yeah, that sounds really good. And I think this brings me really to the next question, which is, how do I get started?
Perfect. Yeah, if you want to throw up a slide, I've moved us onto our kind of QR code that takes you to a web page which will bounce you through to a sign up page. So you can either take a photo of that and go via the QR code route, or if you search for Core Wireless and Microvisor sign up, then you'll find the page I've linked here. And there's a form that you can fill in there to kind of express your interest, and one of the team will kind of reach out and speak to you. And if Microvisor is something that you can make use of, and maybe you want to get up and running, maybe you've got some existing code, or you've got a project that could benefit from some of the things that we've talked about today, then we can get you one of the dev boards that you can see on the screen here. So this is our Nucleo form factor dev board, which contains the STM32U5 IC, the kind of black one in the middle there. It contains a cellular modem and a super SIM that enables cellular connectivity, and it contains a Wi-Fi radio and Ethernet module as well. So if you've got a Wi-Fi, Ethernet, or cellular connected application, then you can pretty much port it to the U5 and then push it with Microvisor, and you can get up and running. And we've had several prospects that have kind of filled in that form, got their hands on one of these dev boards, and they've got their application running up the same day, really. So it can be very, very straightforward to kind of get up and running and get debugging your application.
Sounds really good. So if you have any questions, I'm talking to the audience who's watching us right now, feel free to drop the questions in the comment section. And I'm sure that Randy and Jonathan would be more than happy to answer your questions. In the meantime, this has been really excellent and so much information. Thank you very much, and thank you very much, Randy, for doing the demo for us. And now I would like to ask you both if you have any last words, any call to action for all the engineers who are watching us.
I would just like to say, thank you, Alina, for hosting, and I hope it's been of interest to people. And yeah, if if anyone wants to kind of learn a bit more about a microvisor architecture, then there's lots of information that we've put out there. So if you search for microvisor, a core microvisor, then you should find all of that information. Documentation is all public, so you can take a look and look to get started. And we kind of we look forward to kind of helping people build secure connected IoT devices, really.
Thank you. Yeah, what about you, Randy? Anything from your side? I really enjoyed your demo.
Thank you. Yeah, it's always a pleasure to give, and no matter how many times I give it, just the fact that all those pieces work and they work so seamlessly is really refreshing to think about all the possibilities, as Jonathan mentioned, of how you can shift the mentality of how you build your app, how you iterate on your app, and how you take care of customer issues should they arise in the field. It's just really really powerful.
Yeah. So I think, I come from a, let's say, more cloud-focused background, and I've only relatively recently started on the embedded side. So I think for me, at the very beginning of my embedded journey, it was still quite shocking how much of a difference in the way of working there is between cloud engineers or just even, just software engineering in general, and agility in software engineering versus how things work on the embedded side. So this is why it's really great to see the tools that are available to developers like Microvisor, to just accelerate the journey. And I think this is really, really great to see. So thank you very much for being here today.
Thank you very much for hosting us.
Yeah, thank you.
It was a pleasure. And I wish you all a very nice rest of your day. And also for the engineers out there, join us next time on our next episode. Bye.
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 Bye.